Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. We will be talking about molecular orbital theory part 2 under the paper Atomic, Molecular and Laser Spectroscopy. After completing this module, we will be able to learn diatomic molecular orbitals, energy level diagram for molecular orbital, and electronic configuration of molecules in the molecular orbital theory concept. Diatomic molecular orbitals. The molecular orbital theory regarding the bonding in hydrogen ion and hydrogen molecules can be extended to other homonuclear diatomic molecules as well. In general, molecular orbitals are classified in terms of their symmetry about internuclear axis. Since the atoms A and B are identical, the midpoint of A-B bond is a center of symmetry for the molecule. Further, if an inversion of the molecular orbital about the center of symmetry doesn't change the sign psi, it is said to be even and it is denoted by the symbol G as a subscript. In case the sign changes, the orbital is said to be odd and a subscript U is assigned to the symbol. So it is to note that G and U stand for the German words grade means even and ungrade which means odd respectively. Case 1, combination of two s orbitals. The combination of two 1s orbitals gives rise to the formation of a bonding 1s sigma and an anti-bonding 1s sigma star orbitals. There is a buildup of electron charge between the nuclei leading to the formation of a bond in the case of bonding orbital and a depletion of charge between the nuclei in the case of anti-bonding orbital. In the above notation, the bonding and anti-bonding orbitals are respectively denoted by 2s sigma G and anti-bonding 2s sigma U star, molecular orbitals of the same shapes as 2s sigma G and 2s sigma U star orbitals. Case 2, combination of s and px orbitals. As orbitals may combine with a p orbital if the lobes of the p orbital point along the internuclear axis. A bonding molecular orbital result when the adjacent lobes have the same sign and an anti-bonding molecular orbital when the adjacent lobes are of opposite sign. Figure depicts the combination of s and px atomic orbitals. The figure tells the s and px atomic orbitals. In the first part, s and px orbitals have been shown. Px with one positive sign here and negative sign here, and in the second negative sign this side and the positive sign this side, and then writing psi a 1s minus psi b px and psi a 1s plus psi b px. So the molecular orbitals correspondingly sigma G and sigma U are framed and have been shown in this figure. Case 3, combination of two p orbitals. The two lobes of each of the three p orbitals have opposite sign. If the internuclear axis is taken as the x direction, 2px atomic combine to give the MOs as 2px sigma G, 2px sigma U star as has been depicted in the figure. Both have symmetry about the bond axis. However, the combination of two py orbitals gives the molecular orbitals 2py pi U and 2py pi G star. It is again shown in the figure. Now, because both of these have the same energy, these are doubly degenerate. The py pi U molecular orbital consists of two streamers, one above and one below the nuclei. And in this case, the bonding orbital is odd and the anti-bonding orbital is even, unlike the earlier ones. The figure depicts the formation of bonding orbital 2py pi u and the anti-bonding orbital 2py pi g star from two py orbitals. Combination is the same for py orbitals. And it is noteworthy that in the combination of atomic orbitals, the possibility for the combination of 1s and 2s atomic orbitals or s and p orbitals of two identical atoms is not possible because their energies are completely different. Energy level diagram for molecular orbital. Let the molecular orbitals are arranged in the increasing order of energy. The energy levels of molecular orbitals of diatomic molecules resulting from 2p orbitals are somewhat uncertain as the atomic number of the atom increases. Also, for molecules lighter than oxygen, the 2p pi nu orbitals lie higher than the 2p sigma g orbitals, but for molecules heavier than oxygen, the 2p pi u orbitals are of lower energy than 2p sigma g orbitals. The figure here depicts the molecular orbital energy level diagram for homonuclear diatomic molecules, heavier than oxygen molecule and lighter than oxygen molecule. R.S. Mulliken has suggested an alternative terminology for the orbitals 2s sigma to 2p sigma star, and its sequence is z sigma 2s sigma less than y sigma 2s sigma star less than s x sigma 2p x sigma less than w pi 2py pi is equal to 2pz pi less than nu pi 2py pi star is equal to 2pz pi star less than u sigma 2px pi star. The bracket gives the earlier notation as 2 sigma and 2px sigma, etc. This notation is being used for 1 quantum and 3 quantum molecular orbitals by writing k and m before the Mulliken symbol. Thus k, z sigma stands for 1 sigma, 1s sigma, m, y sigma for 3s sigma star, and like that. Electronic configuration of molecules in the molecular orbital concept. Electrons can assign to the orbitals following the Pauli's exclusion principle after the molecular orbitals are obtained. The molecular orbitals of the lowest energy are filled first, and each molecular orbital can get 2 electrons of opposite spins, and in case of degenerate orbitals, Hund rule is going to be applied. Homonuclear diatomic molecules like hydrogen. The number of electrons in hydrogen molecule is 2. The molecular orbital 1s sigma is formed from 2h 1s atomic orbitals. As both the electrons are in the lowest bonding molecular orbital, the 2 electron bond of hydrogen molecule is stronger than the 1 electron bond of hydrogen ion. So 2h 1s 2 hydrogen 1s sigma g square. In case of helium 2, the overlap of 2 helium 1s orbitals gives a bonding 1s sigma g and anti-bonding 1s sigma u star. Molecular orbitals with 2 electrons in each. The superposition of 2 electrons in the bonding orbitals and 2 in the anti-bonding orbitals leads to no bonding. Hence, helium 2 molecules does not exist under normal conditions. So, twice of hydrogen 1s2 gives you helium 1s sigma g2 1s sigma u star. Beryllium atom has 4 electrons, making a total of 8 electrons for the beryllium molecule. They are distributed as Be2, Kk 2s sigma g square 2s sigma u star square. As the presence of equal number of bonding and anti-bonding electrons produces no net bonding effect, the molecule is not likely to exist. So that is the reason that Be2 doesn't exist. Boron, the 10 electrons in this molecule are distributed as B2, Kk, 2s sigma g square, 2s sigma u star square, 2p sigma g square, 2p sigma g and 2p pi u molecular orbitals have nearly the same energy. Therefore, instead of 2p sigma g square, the alternate configuration 2p sigma g1, 2p pi u1 leading to a total spin of 1 is also possible. These two unpaired electrons per molecule lead to the observed paramagnetism of boron molecule. Carbon molecule has 12 electrons. The electrons are distributed as C2, Kk, 2s sigma g square, 2s sigma u star square, 2p sigma g square, 2p pi u square. The orbital 2p pi u is doubly degenerate. According to Hund's rule, the term with the highest total spin will have a lower energy. If both the electrons occupy one of the degenerate molecular orbitals, their spins must be anti-parallel, giving a total spin of 0. However, if one electron is in one of the degenerate molecular orbitals and the other electron in the other molecular orbital, their spins will be parallel, giving a total spin of 1. So this term will be the lowest. As 2p pi u and 2p sigma g molecular orbitals have nearly the same energy, an alternate ground state configuration is also possible, like Kk 2s sigma g square, 2s sigma u star square, 2p sigma g 1, 2p pi u cube. In this configuration also, two of the electrons will have their spins parallel, giving a net spin of 1, leading to a triplet term. Nitrogen molecule. The 14 electrons in the nitrogen molecule are distributed as Kk 2s sigma g square, 2s sigma u star square, 2p sigma g square, 2p pi u 4. The bonding orbitals 2s sigma g square, 2p pi u 4 are not cancelled by the corresponding anti-bonding orbitals. These 6 bonding electrons give triple bond n is equal to n, one bond being sigma and the other two are pi bonds. In this configuration, a strong bonding is expected as it has 8 bonding and 2 anti-bonding electrons apart from the k electrons. So as nitrogen has 2 more bonding electrons than C2, its dissociation energy is expected to be larger, which is confirmed by experiments. Coming to the oxygen molecule, the oxygen molecule has 2 more electrons than nitrogen molecule. And since the next molecular orbital 2p pi g star is degenerate, the 2 additional electrons will go in these anti-bonding orbitals, one each with parallel spins, called the Hund's rule. And this gives the electronic configuration as Kk 2s sigma g square, 2s sigma u star square, 2p sigma g square, 2p pi u raised to the power 4, 2p sigma g star square. As electrons in the last degenerate orbital have parallel spins, the oxygen molecule becomes paramagnetic, which is again confirmed experimentally. Fluorine molecule. There are 18 electrons in the fluorine molecule, and these can be arranged as F2 configuration as Kk 2s sigma g square, 2s sigma u star square, 2p pi u raised to the power 4, 2p sigma g square 2p pi g star 4. The inner shell is non-bonding and the field bonding 2s and 2p orbitals are cancelled by the corresponding anti-bonding orbitals. This leaves a sigma bond from the bonding orbital 2p sigma g. The bonding in chlorine and bromine is analogous to that in fluorine molecule, except that the inner two shells or the inner three shells of electrons are full. Neon Ne2. For Ne2 we have Kk2s sigma G2, 2s sigma U star 2, 2p pi U raised to the power 4, 2p sigma G2, 2p pi T star 4, 2p pi U star 2. As the system contains equal number of bonding and anti-bonding electrons, there is no chemical bonding in agreement with the experiment. So, in the same manner, one can describe homonuclear diatomic molecules formed from atoms of the next period. So, bonding molecular orbitals produce large building between the nuclei, and anti-bonding molecular orbitals produce charge depletion between the nuclei. Therefore, removal of an electron from an anti-bonding molecular orbital increases the dissociation energy dE or decreases the bond length of the bond, whereas removal of an electron from the bonding molecular orbital decreases dE or increases the bond length. So, for example, the highest filled molecular orbital in oxygen increases the dissociation energy from 5.08 to 6.48 electron volt, and in nitrogen removal of electron from the highest filled bonding molecular orbital decreases the dissociation energy from 9.91 to 8.85 electron volt. As the energy is always required to ionize a stable molecule, the removal of bonding or bonding electrons decreases the total molecular energy. So, heteronuclear diatomic molecules, effective combination of atomic orbitals from two different atoms is possible only if they have similar energies, sufficiently overlapping charge clouds, and the same symmetry properties with respect to the internuclear axis. So, in this case, depending upon the energy, 1s of one atom may combine with 2p of another, and so on. So, we shall be considering some examples like HF. In this case, the energy levels of AOs of the two atoms are not equal, and some MOs will contain a large contribution from one constituent AO than the other. The electronic configuration of hydrogen and fluorine atoms are H 1s1 and F 1s2, 2s2, 2p5. So, from spectroscopic studies, it is found that the 1s orbital of hydrogen and 2p orbitals of fluorine have comparable energies, and therefore, the 1s2 and 2s2 electrons of fluorine remain in atomic orbitals only. As the internuclear axis is taken as the x-axis, the hydrogen 1s orbital allows a greater overlap with the 2px fluorine orbital than that with 2py or 2pz orbital. The figure part A depicts the overlapping orbitals have the same sign and hence give a bonding molecular orbital, while the figure B represents the hydrogen 1s is overlapped by both the lobes of the py orbital of fluorine, so that the bonding and anti-bonding effects are cancelled. We are talking about the HF molecule, H1s and F2px, or H1s and F2py. The overlap between H1s and F2px orbitals is responsible for the bonding orbital 2px sigma. The rest of the electrons in fluorine remain in the 2py, 2pz atomic orbitals, and the electronic configuration of HF is written as K 2s2 2px sigma 2py square 2pz square. NO. Nitrogen and oxygen are close to each other in the periodic table, and therefore their atomic orbitals are of similar energy. The nitrogen atom has 7 electrons and the oxygen atom has 8. The energy levels of the various molecular orbitals are the same as for homonuclear diatomic molecules. So consequently, the electronic configuration is Kk 2s sigma 2, 2s sigma star 2, 2p sigma 2, 2p phi 4, 2p pi star 1. So the inner shell is non-bonding and anti-bonding. 2s sigma and 2s sigma star orbitals cancel, leaving a sigma bond, a full pi bond and a half pi bond from 2p. The molecule is paramagnetic since it has an unpaired electron, and removal of an electron from the system means the removal of an electron from an anti-bonding orbital. Hence, the bond in NO plus is expected to be shorter and stronger, which is indeed the case. Compare the molecular orbital wave function of hydrogen molecule with that of the valence band theory. As we have the equation that gives the molecular orbital wave function, where the Heteronuclear function for hydrogen molecule can be written as psi MO is equal to constant psi A1 psi A2 plus psi B1 psi B2 plus psi A1 psi B2 plus psi B1 psi A2, and psi HL is equal to, corresponding to Heteronuclear function, constant psi A1 psi B2 plus psi A2 psi B1. The first two terms in above equation represent the possibility of both the electrons being on the same proton at the same time. These represent the ionic structures Ha minus, Hb plus, Ha plus, Hb minus. The third and fourth terms represent the possibility in which the electrons are shared equally by both the protons, and hence they correspond to covalent structures. Both the terms in the valence band wave function correspond to covalent structures, as one electron is associated with one nucleus and the second electron is associated with the other nucleus. Write the electronic configuration of sodium and sulfur molecules in the molecular orbital concept. The electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. This is standard electronic configuration. Now, in molecular orbital terms, Kk 2s sigma square, 2s sigma star square, 2py pi is equal to 2p z pi raised to the power 4, 2px sigma square, c 2px sigma star square, 3s sigma square is equal to kk 3s sigma square, 3s sigma star square. So the electronic configuration of sodium molecule can be written like this. This result may be compared with the electronic configuration of lithium molecule, which is another alkali metal. Now, for the electronic configuration of sulfur, which is 1s2, 2s2, 2p6, 3s2, 3p4, and the electronic configuration of sulfur molecule is Kk 3s sigma square, 3px sigma square, 3py is equal to 3pz pi raised to the power 4, 3py pi star is equal to 3pz pi star square of it. Now the orbitals 3py pi star is equal to 3pz pi star can accommodate 4 electrons. There are only 2. Hence, by Hund's rule, one electron will enter each of these with their spins parallel, giving a paramagnetic molecule. Let us sketch the molecular orbital formation in ethane and ethylene. Ethane is written as C2H6. In ethane, each carbon atom is sp3 hybridized. 3 of these hybridized orbitals in each carbon atom overlap with the s orbitals of 3 hydrogen atoms, and the fourth one with the corresponding one of the other carbon atom. All the bonds are represented by the figure. In case of ethylene, The chemical structure is C2H4. Each carbon atom is sp2 hybridized. Two of these form localized sigma type molecular orbital by overlapping with 1s orbital of hydrogen atom, and the third overlaps with the second carbon, forming another localized sigma MO. These three sigma bonds lie in a plane, the molecular plane. Each carbon atom is left with a singly occupied p orbital with its axis perpendicular to the plane of the molecule. The lateral overlap of these two p orbitals gives a pi bond, the second bond between the two carbon atoms, the plane of the molecule in the nodal plane of the pi orbital. So, summarizing, what we have learned in this model is diatomic molecular orbitals, energy level diagram for molecular orbitals, and electronic configuration of molecules in the molecular orbital concept. Thank you.